Hello everyone, this is the third lecture of this week. Last class we discussed how to construct the stiffness matrix for bar element. Same exercise we will do it for beam today. Okay. So, what we have now is if you recall, we have considered a problem. Now, this is take an example of this problem. This is a bar, this is a beam which is subjected to some load, say for instance a concentrated load, right. Okay. Now, we want to solve it. Now, please make note one thing I have mentioned in the last class as well. See, there are many approaches you can construct, you can arrive at the stiffness matrix, final stiffness matrix. But the approach what we are following is the very simplest approach, and the reason is our objective here is to extend whatever information we have, whatever knowledge we have on matrix method of structural analysis and also in solid mechanics and strength of material. Our objective is to based on that knowledge, we just expand the application of that knowledge and then see look beyond for possibilities of having a general methodology for solving structures and different continuum, and that is what we are doing. So, now similarly first we have to discretize it, we have to discretize into several segments. For instance, let us discretize into several segments, let us 4, same as the matrix direct stiffness matrix. We have these are the node numbers and then corresponding these are the member numbers, right. And then for any representative element we have to construct what is the stiffness matrix, right. Now, take a representative element, for instance this is a representative element, okay, which is this is one node and this is another node. Now, if you in the bar element we had just 1 degrees of freedom, and that degrees of freedom is the deformation along the longitudinal axis. But in beam, recall in direct stiffness matrix also we discussed per node we have 2 degrees of freedom. One is transverse displacement, another one is the rotation. Now, as per our sign convention, the sign convention that we are using is this. This is this. Now, this is transverse deflection in this direction, we have a transverse deflection in this direction, and then we have rotation, anti-clockwise rotation is positive, anti-clockwise rotation is positive. So, essentially we have, say it is V1, and this is theta 1 and this is V2 and then theta 2. Okay. So, these are 4 degrees of freedom we have. Now, what is our objective is to construct the stiffness matrix such that this stiffness matrix relates these 4 degrees of freedom and the forces associated with these degrees of freedom. Okay, before that, if you see, let us see how if we have a beam, for instance, if we take a beam like this, and it is subjected to some loading, say for instance some loading m, and this is the longitudinal axis of the beam. Okay. And then what happens, the beam bends like this. If I take any segment, then this beam bends like this, right. Now, then if we take any axis, suppose this is the neutral axis of the beam, this is the neutral axis of the beam, okay. And then if we take any axis, for instance this axis, if we take, which was we all are using the Euler-Bernoulli assumption that the for plane section normal to the neutral axis remain plane even in the deformed configuration, right. Now, in that case you see, so what happens is at the neutral axis your longitudinal displacement is 0. Now, one assumption is whether you take this point or this point, as far as transverse displacement is concerned, the transverse displacement will be same, and this transverse displacement is, suppose the transverse displacement here, this transverse displacement is V. So, Vx Vx give you the transverse displacement at any point. Okay. Now, then what will be the slope? Slope at any point theta will be dv dx. Okay, dvx dx, that will be slope. Now, so this transverse displacement will be same for this point and this point. Now, but what happens to the longitudinal displacement? You see, at the neutral axis your longitudinal displacement is 0, if the longitudinal displacement say is u. At the neutral axis your longitudinal displacement is 0, but if you move away from the neutral axis, this longitudinal displacement will be, suppose this is z, this is across the cross section, this is z axis, suppose this is z axis. So, along the at the neutral axis this longitudinal displacement will be 0, but if you move away from the neutral axis, suppose the longitudinal displacement, this is the longitudinal displacement. Okay. This is the longitudinal displacement. This longitudinal displacement can be written as u is equal to minus z into dv dx. Okay. dv dx, this is the longitudinal displacement. Now, if we calculate v, then you see if we know v, then we know what is the longitudinal displacement from this relation. If we calculate v, we also know what is the expression for theta, expression for slope. Okay. So, the major thing is to start with our objective is to calculate what is the v. Now, if you recall, in the case of truss, we started with an assumption of the displacement field. For instance, in the case of truss, at one point if your deflection is u1, another point your displacement is u2, then we defined a function between point 1 and between point 2. This function gives us how displacement varies along the length of that element. Okay. Now, in that function, if we substitute x1, then we will get u1, and if we substitute x is equal to x2, we will get u2, the nodal values. Same exercise we will be doing it here. Now, assume, the first is, suppose assume Vx is equal to say a polynomial expression, say a plus bx plus cx square plus dx cube. Now, in the case of truss, if you recall, we just had the linear expression in the first two terms. We did not use the cubic expression. The reason is very simple. In the case of truss, we already see, when you use a polynomial, use an approximation, these approximations always associated with some constants. We have to find out those constants. For instance, here a, b, c, d are the constants. In the case of truss, we had two constants. In order to find out those constants, we need sufficient number of equations. In the case of truss, we had just two equations, and those equations are and what was the premise of that equation? Information about the nodal displacement. We had every node we had just one displacement, two nodes we had two displacement, means two information. That is why with that information we could only calculate two constant. That is why our approximation was linear. But now in this case we had four information. What are the four information? We know what is the transverse displacement, this is v. We know what is the transverse displacement and rotation at node 1, and transverse displacement and rotation at node 2. So, 4 unknown, that is the reason we considered 4 constants here. Okay. So, then in this, so what will be dv dx? dv dx will be, if we this will be b plus then 2 c x plus 3 d x square. So, this is, now let us substitute this equation from the first equation. Suppose this is equation number 1, this is equation number 1 and this is equation number 2. From the first equation we get two, from first satisfy at every node we get two equation, we satisfy equation this at both nodes we get another two equations. So, let us do that. So, it gives me say at x is equal to x 1. So, at x is equal to x 1 we had v of x 1 that is equal to, then we have a plus then we have then x is equal to, okay. Now, let us do one simplification. Suppose instead of x1 and x2, suppose just change the coordinate system, so that our computation will become easier. Suppose this x1 is equal to 0 here and x2 is equal to L here. L is the length of this element. Okay. So, essentially x is equal to x1, then what happens? If you substitute x is equal to 0, then this becomes that V1 is equal to, so this also you can remove. Okay. So, this V1 becomes A. So, this is one expression, and x is equal to x1, this becomes theta 1. So, theta 1 becomes, if you substitute x is equal to 0 here, so then theta 1 becomes B. Okay. So, this is two equation, and then at x is equal to x2, at x is equal to x2 means which is equal to L, this is equal to 0. Then what we have is, we have V2 is equal to, this becomes A plus B L plus C L square plus D L cube. So, this is one equation, and then another equation theta 2, in this expression if you substitute L, B plus 2 C L plus 3 D L square. So, these are all 4 equations we have. So, this is equation number, this is one equation, this is another equation, this is another equation, and this is another equation. These 4 equations, and we have just 4 unknowns. We have to solve these 4 equations for 4 unknown, and if we solve them, then what we get is, we get some expression for A, B, C, D, and then what we have to do, we have to substitute that expression in this equation. Okay. In the same way we did it for truss. If you substitute that A, B, C, D in this expression, and then you write this V in terms of V1, theta 1, V2 and theta 2, then what we have is Vx is equal to, if you write it, say N1 V1 plus N2 theta 1 plus N3 V2 plus N4 theta 2. So, N are the N1, N2, N3 are the safe functions. Okay. These are the safe function, right. Now, so if you substitute A, B, C, D from these 4 equations, and if you substitute them in this, and just like manipulation, you get an expression like this. And in this expression, let me give you the final expression for N1, N2, N3 and N4, and that is that becomes N1 in this become 1 minus 3 x square by L square plus 2 x cube by L cube. N2 become x minus, then 2 x square by L square, 2 x square by L, and then plus x cube by L square. This is N2. N3 become 3 x square by L square minus 2 x cube by L cube, and finally, N4 you can check these values, minus x square by L plus x cube by L square. Okay. Now, we will see later that these we are doing in terms of x and L. This can be done in terms of parametric coordinate system, where it varies from 0 to 1, and those exercises we will see later. So, these are the 4 safe functions. Now, let us plot this 4 safe function. If you have to plot it, then if you recall the properties of safe function, the properties of safe function is that Ni at x j, that has to be delta I j. So, these satisfy Kronecker delta property, right. Now, so let us see that, let us plot this safe function. Now, if I have to plot it, say if I have to plot N1, if I x is equal to 0, N1 will be 1, this, and then x is equal to x is equal to L. If you substitute x is equal to L here, then this will be 0. Okay. So, if you substitute here x this will be 0. Now, similarly, if I plot now I am not plotting what happens in between, I leave it to you, check the expression and then see what is the plot in between. What I am showing you here is that that the safe functions will this satisfy this Kronecker delta property and the other properties that we discussed. Now, what is N2? N2 will be, you see, here it is important, we will come to N2 later. Let us talk about N3 first. Now, N3 is x is equal to 0 if we substitute N3 is 0 and x is equal to L. If you substitute L here, N3 will be 1 and in between it is cubic. Okay. Now, and then finally, we have N4. Finally, N4. Now, what is important here, you see, N2 is associated with, if you look at, okay, before that, we also discussed, if you recall last class, if we take the summation of all these safe function, then it will be 1. Now, you take summation of all n1, n2, n3, n4, any arbitrary value of x, suppose x is equal to 0 or x is equal to 1 or any point, check whether they are 1 or not. Now, what we will see is that n1, these safe functions, in the case of truss, we had two safe functions, one is n1 and another one n2, and both safe functions were associated with similar kind of displacement, right. But here we have two kinds of displacement, one is the transverse displacement, another one is rotation. Now, n1 and n3 are associated with that displacement, transverse displacement, whereas n2 and n4 is associated with rotation. So, when I say that at x is equal to when I say that ni xj satisfy delta ij, it means that for n1 for n2 it means that at x is equal to at that particular point where that n2 is defined, the rotation what you get is that rotation should be 1, right, means it should be, the rotation should be here 1. In this case it is 1, in this case it is 1. What says that this rotation should be 1, this value should be 1. Similarly, here it is saying that this rotation should be 1, means this value is 1, right. Now, I am not plotting it in between what will happen, you follow this expression and then plot it, and another exercise you have to do, you take any arbitrary point at x, any value and then see sum them whether you get a 1 or not. If you get 1, then it satisfies the property, but if you do not get 1, does that mean that it does not satisfy the Kronecker, the partition of unity property? And if you do not get 1, try to find out why you are not getting it 1. Okay. So, these are the expression for safe function. Now, next is, once we have the safe function, if you recall in the case of truss, we have to find out what is the strain displacement. So, these safe functions give you how from this safe function we can obtain the strain displacement relation, right. Now, before that, let us now discuss what kind of strain we need to incorporate in this formulation. If you look at, just now we discussed here that epsilon u transverse this displacement is u is equal to minus z into del v del x. So, then longitudinal strain will be, what will be the longitudinal strain? Then longitudinal strain will be epsilon is equal to du dx, which essentially becomes, if we substitute that, minus z into d2v dx2, right. This is the longitudinal strain. Now, let us, now we already know expression of v as a function of n1 as a function of the nodal coordinates, then substitute this expression or v in this equation, and if you do that, let us see what we get. Now, so we have epsilon is equal to, say, epsilon is equal to minus z into d2v and then dx2, and then v we have n1 v1 plus n2 theta 2 theta 1 plus n3 v3 plus n3 v2 and n4 theta 2. This is the expression. Now, if we substitute that in this expression, now this can be written as like this. We have say n1, then n2, n3 and n4. These are the shape function, and then here we have the degrees of freedom, which is v1, theta 1, v2 and then theta 2. Okay. Now, let us substitute this v. Let us substitute v from this to this expression, and if we do that, epsilon will be minus z, and then this will be d2 n1 dx2, just the second derivative of this d2 n2 dx2 dx2, and then and then d2 n3 dx2, and then finally we have d2 n4 dx2. This is for this part, and then we have these degrees of freedom v1 theta 1 v2 theta 2. Okay, right. So, this is the expression. Now, we already know the expression for n1, n2, n3, n4. Now, if we substitute that expression in this equation, the equation what we get is minus z. This is the this. Okay, let me just write the expression here. What we get is from n1. If we this n1 will get minus 6x by L square, minus 6x by L square, sorry, minus 6 by L square, and this gives you 12, this gives you this x cube, this gives you 12x by L cube, right. So, this becomes minus 6 by L square and plus this become 12x by L cube. So, L cube, this is for first one n1. Similarly, we can have for n2, n2 is this part will be 0, this part will becomes minus 4 by L, and this part become 6x by L square. So, this becomes minus 4 by L and then 6x by L square, we have plus. Okay. This is for this. Similarly, for the third one, this becomes 6 by L square and this becomes minus 12x by L cube. So, this becomes 6 by L square and then minus 12x by L cube, right. And finally, this becomes minus 2 by L and this becomes 6x by L square. So, minus 2 by L plus 6x by L square. Okay. So, this is, and then finally, here we have v 1 theta 1 v 2 and theta 2. This is epsilon, right. Now, so this is, you recall that epsilon is equal to some matrix B into displacement, that was strain displacement relation, and then what is here B matrix is this part, the entire part is B, right. So, we have B. Now, then what will be D? Now, once we have B, now if you recall the stiffness matrix, the general form of the stiffness matrix was what? K is equal to the element stiffness matrix was integration over the entire domain, entire volume, then we have B transpose, then D, the constitutive relation, and then B, and then integration over the entire domain, right. That was our stiffness matrix. Now, we have obtained B already this. So, B we can get from this. What is D? Now, you see what we are only talking about, we are only considering this longitudinal strain, because this longitudinal strain has all the information about the deformation, right. So, this longitudinal strain, then we have just considered this one component of strain along the longitudinal directions. Then what will be the corresponding stress? Corresponding stress will be just along the longitudinal direction, and what will be this stress and strain relation? This stress and strain is related through Young's modulus, because it is just one longitudinal strain we are talking about, and then integrating over the entire volume, right. Now, so if this is, then our in this case then B will be D will be is equal to Young's modulus E. Now, then finally, what we have to do is we have to substitute this expression here, and let us do that. Let us substitute that. So, then K will be, then K. So, K will be integration over the entire volume, and this will be that the B transpose. Let us not writing it once again, you know that, and this Young's modulus and then B, right, and d omega. Now, this how we are integrating this? We are integrating this once again. Let me come to this beam. Please note, what we are essentially doing, we are taking a longitudinal section, a longitudinal fiber along the longitudinal direction, considering only the transverse, considering only the longitudinal strain, because that longitudinal strain has information about the transverse displacement and the slope. So, we are considering the longitudinal direction, and then that strain is here epsilon, and this is, and that is why we have just only one d is equal to a scalar, a Young's modulus. Then when we integrate it, that integration has to be done not only along the length, that integration has to be done along the cross section as well, right, because along the cross section your longitudinal strain will be different. The strain depends on z, which depends on what fiber, what longitudinal fiber we are considering. So, in this case, this integration will be first along the cross section and then along the length. Along the length means 0 to L in this case. So, this becomes, let us write it, B transpose is, I am writing it because then 12 x and then minus 6 by L square, then we have 6 x by L square and then minus 4 by L. Please check these values, 6 by L square minus 12 x by L cube, and then finally 6 x by L square and then minus 2 by L. So, this is for B transpose E, and then another we have the same thing as this. Okay. This integration will be over d A and then over d x. Okay. Now, so this is the stiffness matrix. Now, let us and then there will be a z also, then it will be E we can take outside, E is constant and there will be a minus z term. Okay. Now, if we perform this integration over x over the length as well as across the cross section, means over z from minus say minus h to h, depends on how you represent the depth of the beam, and if you do that, then what you get. But remember one thing, in this expression we will get an expression like we will get an expression like this integration over. Okay. So, we have minus z for this and then another minus z for this. Okay. Another minus z for B. So, this is for B transpose, this is for B. So, you see, look at this term, you will get an expression something like this z square dA. If you integrate, once the integration along the length is performed, then all you can take outside and then we are left with something. So, K will be something, say some phi into this. This phi is the integration of the entire thing along the length. Now, what is this z square dA? Z square dA is essentially, if you recall, z square dA is second moment of area, right. Now, if you substitute second moment of area here and then do this integration once again, then the stiffness matrix, the expression for stiffness matrix will get E for from this, and I because z square dA is equal to I, EI, and L you get from this expression EI by L cube, and then the term will be, it will be 12 and then 6 L. By now, you have understood what is the form that we are going to get, because you have seen this form many times, right. 4 L square minus 6 L 2 L square, and this becomes minus 12 and then minus 6 L 12 once again minus 6 L, and finally 6 L 2 L square and then minus 6 L and 4 L square. Yes, this was the stiffness matrix for, you have obtained this stiffness matrix, you are familiar with this stiffness matrix because we have seen it in case of in direct stiffness matrix method for beam member, right. Now, but at that time we derived this matrix based on the directly based on the load displacement relation, based on the how the moments and curvature is related and the load and displacement is related with each other. Based on that, we directly obtained this matrix. We did not follow this approach, okay. But as I said in the last class, this approach has a flexibility to determine stiffness matrix, construct stiffness matrix for a more general class of elements. These are the some elements we are considering just to establish the fact that the final outcome of the stiffness matrix will be the same as the stiffness matrix we had for direct stiffness matrix in the direct stiffness matrix method. And another reason why you are following this approach, because as I said, it is in extension, because you already had the knowledge of direct stiffness method, you had the knowledge of strength of material and solid mechanics. It is just based on the knowledge, we are just trying to see whether a more general perspective, more general formulation of stiffness matrix can be obtained or not, which is applicable for a more general class of elements. So, this is for beam element. Now, next class what we do is, next class for truss element, calculating nodal load vector was not, it was very straightforward. But recall in the case of beam element, for in the direct stiffness matrix method, for beam element how we calculated the equivalent joint load. First we had to find out the fixed end moments, and then you apply the equilibrium at different joints to get the equivalent joint load. We will see here next class using again the same the general form, how these nodal load vector can be constructed, and then that will be for beam, and then from the subsequent classes we will see, we will apply this concept to construct stiffness matrix for a more general class of elements, for two dimensional elements. Okay. With this I stop here today. See you in the next class. Thank you.